Welcome! In this video, we'll dive into an interesting problem, number 439 ternary expression parser. We'll explore how to parse a ternary conditional expression to evaluate its results step by step using efficient algorithms. Let's get started. In this problem, we are tasked with implementing a function to parse and evaluate a ternary expression represented as a string. A ternary expression follows the format condition: true_value, false_value. Here, the condition is always a single character, either T or F, representing true or false, respectively. The true_value and false_value can be single characters, like digits between 0 and 9, or even another ternary expression. To evaluate such an expression, we simply check the condition. If it's T, we return the true_value. Otherwise, if it's F, we return the false_value. The input is guaranteed to be a valid ternary expression of length between 1 and 10,000, and the output will be a single character as the result of evaluating the expression. Let's look at some examples to understand this better. In the first example, the input expression is T, 2:3. The condition here is T, which means true. So, we evaluate the true_value, which is 2, and that becomes our result. Therefore, the output is 2. Now, in the second example, the expression is F, 1T, 4:5. The outer condition is F, meaning false. This leads us to evaluate the false_value, which is the ternary expression T, 4:5. In this inner expression, the condition is T, so we evaluate the true_value, which is 4. Thus, the final output is 4. In the third example, the expression is T, F, 5:3. Here, the outermost condition is T, so we evaluate the true_value, which is the nested ternary expression T, F5. In this inner expression, the condition is again T, meaning we evaluate its true_value, which is F. Therefore, the result of the entire expression is F. This example demonstrates how nested ternary expressions are resolved step by step, starting from the outermost condition and moving inward. To summarize, the constraints ensure that the input length is between 1 and 10,000 and that every expression is valid. The conditions are always T or F, while the true and false values are either single digits or valid ternary expressions. There are a few important edge cases to consider. First, nested ternary expressions, like T, F5, F, 2:3, require careful evaluation of multiple levels. Second, simpler single-level expressions, such as T, 1:0, should also work seamlessly. Third, for very large input sizes near the upper limit, the solution must remain efficient. Finally, it's crucial to handle cases where all conditions are the same, like T 1:2 to 3:4, as well as those with false conditions, such as F, T 1:2, F, 3:4. These scenarios ensure the parser is robust and handles all possible inputs correctly. To parse a ternary expression, one intuitive method is a brute force approach using recursive parsing. The idea here is to break the expression into three distinct components: the condition, the true branch, and the false branch. We evaluate the condition first, and based on its value, we recursively process either the true or the false branch. The process begins by identifying the first question mark to separate the condition from the branches. Once the condition is evaluated, we continue this recursive breakdown for deeper nested expressions. However, this method comes with trade-offs. The time complexity can be inefficient, reaching O(n) squared, because extracting substrings during each recursive step can take O(n) time. Additionally, the recursion stack consumes O(n) space, which can lead to stack overflow for deeply nested expressions. While simple to implement, this approach struggles with performance on large or complex inputs. Now, a more efficient solution involves a stack-based iterative parsing approach. This method eliminates recursion and processes the expression iteratively from right to left. Why traverse in reverse? Because the ternary operator is right associative, meaning deeper nested expressions are evaluated first. Here's how it works: as we traverse the string, we use a stack to store the results of true and false branches. When a condition is encountered, we pop the top two values from the stack, evaluate the condition, and push the result back onto the stack. By the end of the traversal, the stack contains just one value, the final result of the expression. This approach improves upon the brute force method by reducing time complexity to O(n), as each character is processed only once. Space complexity remains O(n) due to the stack usage, but it avoids the overhead of recursive calls. While slightly more complex to implement, the efficiency gain makes it well suited for deeply nested expressions. There are also alternative approaches to consider, though they are less commonly used. For example, a deque-based method works similarly to the stack-based solution but allows for handling branches at both ends. However, it doesn't offer significant advantages over the stack approach. Another possibility is pre-processing and simplifying the expression iteratively, replacing evaluated ternary sub-expressions with their results. While easier to understand for small inputs, this method is less efficient overall. Ultimately, we chose the stack-based iterative parsing as the optimal strategy. Its efficiency in handling deeply nested expressions stems from its alignment with the ternary operator's right-associative nature, allowing inner expressions to be resolved before outer ones. This approach reduces time complexity from O(n)² to O(n), and avoids the recursive stack growth, making it a clear winner for both clarity and performance. While slightly more intricate to implement, the trade-offs are justified for handling large and complex inputs effectively. In this problem, we're tasked with evaluating a ternary expression string recursively. A ternary expression follows the format of a condition, followed by a question mark, then a true value, a colon, and finally a false value. The condition is a Boolean expression, represented as T4 true or F4 false. The true value and false value can either be constants, like numbers, or they can themselves be nested ternary expressions. For example, given the input T, F 1, 2, 3 foot, our goal is to evaluate this expression step by step and return the final result. To solve this, we'll break the problem into manageable steps. First, we need to understand the structure of the input. The input is a string that represents the ternary expression, and each expression can include nested sub-expressions. Next, we identify the base case. When the input string is a single constant, such as 1, 2, t, or f, we simply return it directly since there's nothing more to evaluate. Now, we move on to parsing the expression. The first step is to locate the first question mark in the string. This question mark separates the condition from the rest of the ternary expression. Because expressions can be nested, we need a stack to correctly match each question mark with its corresponding colon. By using the stack, we can ensure that we're correctly identifying the boundaries of the current ternary operation, even when nested expressions are involved. Once we've identified the boundaries, we split the expression into three parts: the condition, which is everything before the question mark, the true branch, which is the part between the question mark and the colon, and the false branch, which is everything after the colon. With the expression divided, we evaluate the condition next. If the condition is t, we recursively evaluate the true branch. If the condition is f, we recursively evaluate the false branch. This process continues until we reach the base case, at which point we return the result of the evaluation. This approach relies on a few key insights. First, the problem lends itself naturally to recursive decomposition. We can break the ternary expression into smaller subproblems and solve each one recursively. Second, the use of a stack is crucial for handling nested expressions. It ensures that we correctly match each question mark with its corresponding colon, even in deeply nested cases. Third, the algorithm is efficient because it evaluates only the necessary branch. For example, if the condition is true, we skip evaluating the false branch entirely, saving both time and resources. Finally, we need to account for edge cases, such as single constant expressions like 1, deeply nested expressions like t, f, 1, 2, t, 3, 4 foot, and invalid inputs where the syntax is incorrect, such as missing question marks or colons. To implement this, we use two main data structures. The first is the stack, which helps during parsing to match question marks and colons. The second is the recursion stack, which implicitly handles the evaluation of smaller sub-expressions as we break the problem down. Let's walk through an example to see how the algorithm works. Consider the input t, f, 1, 2, 3 foot. First, we parse the expression. The condition is t, the true branch is f, 1, 2 foot, and the false branch is 3. Since the condition is t, we evaluate the true branch next, which is f, 1, 2 foot. In this second parsing step, the condition is now f, the true branch is 1, and the false branch is 2. Since the condition is f, we evaluate the false branch, which is 2. At this point, we've reached a constant value, so the final result is 2. Analyzing the complexity of this solution, the time complexity is O(n), where n is the length of the input string. Each character is processed once during parsing. The space complexity is also O(n), in the worst case, due to the recursion stack when evaluating deeply nested expressions. This efficiency makes the approach well suited for handling ternary expressions of various sizes and complexities. This Python implementation solves the ternary expression parser problem using a stack-based approach to evaluate the given expression in reverse order. The parse ternary function begins by initializing an empty stack. It processes the expression string in reverse order, iterating from the last character to the first. Each character is inspected to determine its role in the ternary operation. If a question mark is encountered in the stack, it signifies the start of a ternary condition. The algorithm then extracts the true and false values by removing the next three top entries, true_val, and false_val, and evaluates the condition based on the current character, T4 true or F4 false. Depending on the condition, either the true or false value is pushed back onto the stack as the result of the ternary operation. If the character does not represent a condition, it is a part of the expression and is directly added to the stack. This continues until all characters are processed. Finally, the top of the stack contains the evaluated result of the entire ternary expression, which is returned as the output. This approach is efficient because it simplifies the evaluation of nested ternary expressions by processing them from the innermost to the outermost using the stack. The time complexity is O(n), where n is the length of the expression, and the space complexity is also O(n), due to the stack storage. Here, we are implementing the solution to parse a ternary expression in Java. We start by importing the necessary utilities and defining our class. The core method here is parseTernary, which takes a string expression as input. We utilize a stack to help evaluate the expression from right to left. The loop iterates through the characters of the expression in reverse order. When we encounter a question mark, we know it's time to evaluate a ternary condition. The top of the stack will contain the true value and false value separated by a colon. We remove the question mark, pop the true value, then the colon, and finally the false value. Based on whether the current character is T or F, we push either the true value or the false value back onto the stack. If it's not part of a ternary condition, we simply push the character onto the stack. By the end of the loop, the stack will contain only one value, which is the result of evaluating the entire expression, and we return it as a string. Now, in the main method, we create an instance of the solution class to test our implementation. We define a sample ternary expression, T2:3, and pass it to the parseTernary method. The result is then printed to the console. For this example, since the condition is true, the method evaluates to 2 and outputs it. This main method allows us to verify that our solution works as expected for a simple input. You can test other expressions as well by modifying the expression variable. This setup demonstrates how to use the parseTernary method in a real-world scenario. To begin parsing the expression T1:2, we initialize an empty stack. The process involves iterating through the expression in reverse order, starting from the last character. First, we encounter 2, which is pushed onto the stack, followed by colon and then 1. Each of these characters is added sequentially, building a stack of 2:1. When we encounter question mark, it is also pushed onto the stack. Finally, the character T is processed, which triggers the evaluation of the ternary expression. We pop question mark from the stack, along with the true and false values 1 and 2, respectively. Since T represents true, we push the true value, 1, back onto the stack. The stack now holds the final result, which is 1. Now, we parse the more complex expression f, T1:2:3. Again, we start with an empty stack and iterate in reverse. The first character 3 is pushed onto the stack, followed by colon and 2. Next, we encounter question mark, which is also pushed, and then 1. At this point, we evaluate the inner ternary expression t1 2. We pop question mark, extract the true value 1 and the false value 2, and remove colon. Since t is true, we push 1 onto the stack, replacing the evaluated ternary. The stack now contains 3, 1. Continuing, we encounter colon and finally f, which signals the need to evaluate the outer ternary f1 3. We proceed to evaluate f1 3 by popping question mark, extracting 1 as the true value and 3 as the false value, and removing colon. Since f is false, we push the false value, 3, onto the stack. The final result of this expression is the top of the stack, which is 3. Moving to the next example, we begin parsing t, f1 2, t, 3 4. As before, we initialize an empty stack and iterate in reverse. First, 4 is pushed onto the stack, followed by colon 3, and then question mark. When we encounter t, it triggers the evaluation of the ternary t3 4. To evaluate t3 4, we pop question mark, extract 3 as the true value and 4 as the false value, and remove colon. Since t is true, we push 3 onto the stack. Continuing, we push colon and 2, followed by question mark, and then 1. At this point, we evaluate the inner ternary f1 2. Popping question mark, we extract 1 as the true value and 2 as the false value, then remove colon. Since f is false, we push the false value 2 onto the stack. The stack now holds 3, 2, and we move on to finalize the outermost ternary expression. To finalize t2 3, we push colon followed by t, which initiates the evaluation. Popping question mark, we extract 2 as the true value and 3 as the false value, then remove colon. Since t is true, we push 2 onto the stack. At this point, the stack contains only the final result, which is 2. This concludes the evaluation of the expression, and the final result is the top of the stack, 2. The time complexity of this solution is O(n), where n represents the length of the input string expression. This is because the algorithm processes each character in the string exactly once using a single for loop that iterates in reverse order. Within the loop, various stack operations such as push, pop, and peek are performed. These operations are constant time, or O(1), and do not depend on the size of the input. For every ternary expression, like t1 2, the algorithm performs up to 5 stack operations, popping the true value, the colon, the false value, and then pushing the result back onto the stack. Since these operations occur within the loop and each character is handled only once, the overall time complexity remains O(n). This is consistent across best, average, and worst cases because the loop always processes the entire string, regardless of its structure. The space complexity of the solution is O(n), where n is the length of the input string expression. This is primarily due to the stack usage. In the worst-case scenario, the stack could hold all characters from the input string. For example, if the input contains no ternary expressions and is just a sequence of values like 1 2 3 4, the stack grows proportionally to the size of the input. For valid ternary expressions, the stack size fluctuates as items are pushed and popped, but the maximum size is still proportional to the input length. Additionally, the algorithm uses a few auxiliary variables, such as char, true_val, and false_val, which require constant space, or O(1). Combining these factors, the total space complexity is O(n) for the stack and O(1) for the auxiliary variables, resulting in O(n) overall. A brute force or naive approach to parsing a ternary expression might involve recursively evaluating each ternary operator. While this method can achieve the same O(n) time complexity, it introduces additional overhead from maintaining the function call stack, leading to higher space consumption. The space complexity in such an approach would also be O(n) due to the recursion depth, which grows with the input size. In contrast, the optimized iterative approach used here avoids recursion entirely. It achieves the same O(n) time complexity by iterating through the input string and using a stack to manage intermediate results. This makes the solution more space efficient because it eliminates the overhead of recursive calls while retaining the same asymptotic efficiency. To summarize, the current solution has a time complexity of O(n) across all cases and a space complexity of O(n), primarily due to the stack. Compared to a naive recursive approach, it's both simpler and more space efficient while maintaining optimal performance. When working with ternary expressions, there are a few common mistakes to watch out for. One of the most frequent issues is improper parsing of conditions. This happens when the condition, true branch, and false branch are not correctly identified, especially in nested cases. A failure to split the expression accurately can lead to incorrect results or even infinite recursion. The key here is to use proper string slicing and ensure any nested parentheses are balanced during parsing. Another mistake is ignoring edge cases. For example, assuming that all inputs are valid ternary expressions can lead to runtime errors or undefined behavior. To address this, always validate the input and handle scenarios like empty strings or malformed expressions gracefully. Lastly, inefficient recursive solutions can cause problems, particularly with large inputs. If recursion isn't optimized, it can lead to excessive calls, slowing down your solution. To mitigate this, consider using memoization or an iterative approach to minimize redundant computations. Another frequent issue involves incorrect base cases in recursion. If the base case for recursion is missing or improperly handled, it can result in infinite loops or stack overflow errors. The solution is to clearly define the terminating condition, such as when the expression reduces to a single value. Additionally, overlooking the precedence of operators can cause errors. Ternary expressions are structured so that only the branch corresponding to the evaluated condition, true or false, is executed. Misinterpreting this precedence can lead to evaluating the wrong branch, resulting in incorrect outcomes. To fix this, make sure your implementation evaluates only the branch that corresponds to the condition and completely ignores the other branch. Paying close attention to these details ensures your solution is both correct and efficient. In interviews, there are some key insights to keep in mind when dealing with problems like this. First, pattern recognition is critical. Many parsing or expression evaluation problems share common patterns, such as recursion or stack-based solutions. The faster you can recognize this, the more time you'll save. Optimization is another focus area. Interviewers often evaluate how well your solution handles large inputs or deeply nested expressions. If your approach isn't efficient, explain how you could adopt iterative or stack-based methods to improve it. Edge case handling is also important. Be ready to articulate how your solution deals with malformed inputs, empty strings, and deeply nested cases. Lastly, your testing strategy matters. Start with simple cases like T1:2, then move on to edge cases such as an empty string or invalid input, and finally test more complex examples like T1:2, F3:4 to ensure your solution is robust. There are several related problems that can help strengthen your understanding of this topic. For instance, LeetCode 439, the ternary expression parser, directly addresses parsing and evaluating nested ternary strings. LeetCode 227, Basic Calculator 2, is another similar problem, focusing on evaluating mathematical expressions while managing operator precedence. LeetCode 394, Decode String, involves parsing and recursion as well, but in the context of decoding nested string patterns. Lastly, LeetCode 772, Basic Calculator 3, is a more advanced variation that includes parentheses and complex operators. Now, when it comes to approaches, recursive parsing is a popular method. It works by breaking the ternary expression into its condition, true branch, and false branch recursively. While simple to implement, it can be inefficient for deeply nested cases. Alternatively, stack-based parsing involves iterating through the string from right to left and using a stack to evaluate the expression. This avoids recursion and is more memory efficient for large inputs, though it can be a bit more complex to implement. Another alternative approach is iterative parsing with two pointers. In this method, you use two pointers to parse the string iteratively, evaluating the condition and moving through the expression step by step. This approach combines the benefits of recursion and stack-based parsing but requires careful implementation to ensure correctness. While it can be faster and more memory efficient, debugging iterative solutions with two pointers can be challenging, especially in edge cases involving deeply nested expressions. Regardless of the approach you choose, it's important to weigh the trade-offs and pick the method that best suits the constraints of the problem you're solving. Great job! We just tackled the ternary expression parser problem by exploring a recursive solution to evaluate the expression effectively. Remember the importance of breaking down problems and applying recursion where applicable. Thanks for watching, and don't forget to like and subscribe for more helpful content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!